Hey, replay viewers, I'm so happy this is my very first mini course that I'm giving, and I hope everybody can hear me. I'm making sure everything's locked in, and if you guys can join me in the chat, that would be awesome. And tell me if you can hear me to make sure all my audio is working well. I am starting, this is my first time on YouTube Live, so it could be a little crazy. I'm not sure. I'm used to Periscope, and so it's a little bit different. So anyway, I have a lot of stuff set up here to talk with you guys about. We're going to be going over the solar storm that happened just the other day. This was a G3 level solar storm, and I've got the source region up here, our beautiful sun, and we're going to be talking about what caused the eruption, what happened as it traveled, what we call in situ, as it traveled out through the interplanetary medium and hit Earth, why the scientists thought that it was going to be slow and therefore maybe not all that exciting, and then it turned into a monster solar storm, and then the aftermath. You know, what happened, what is still ongoing. Believe it or not, the effects of the storm are still ongoing. So I will get into all of that, and I will answer questions. I have some questions that were written in by the Q&A folks on Patreon. So I will be getting to those, and they're very interesting questions. So I'm so excited to be able to talk about them, and then I'll take questions from the field if we have some extra time. Okay, so without further ado, let's get going. Oh, and by the way, just in case this is your first time on any of my live feeds, my name is Dr.Tamitha Scove, and I am a space plasma physicist. I know that's a mouthful, but what that basically means is that I do space weather for a job. And I've been doing this for about 20 plus years, so I've had a little bit of experience in this. And I'm learning more and more every single day from not only scientists and colleagues that have different disciplines and different expertise than myself, but I'm also learning from all of you out in the field who are experiencing space weather firsthand. And I can't tell you how grateful I am to be able to say that that I'm getting educated all over again. It's like I'm in school every single day, and I absolutely love it, and I adore you for it. So thank you so very much. So let's start then. We had a monstrous, in case you weren't, hello, hi, I'm so glad that you guys are now being able to chat and text me. This is great. Hi from Iceland, that's fantastic. And you obviously can hear me. Yeah, I know, propagation is terrible at the moment, yes. And we will talk about why that is still a problem. So let me go into what started this whole thing, okay? We had a huge filament eruption on the sun. Now, a lot of you probably already know that, but this was a very slow filament eruption. And honestly, us scientists, you know, we look at it and went, okay, did it completely erupt? I mean, part of it kind of stayed behind. We weren't really sure because it happened so slowly. In some people's consideration, it was considered a stealthy solar storm because, thank you, hello from Finland and the Netherlands. It was considered a stealthy solar storm because it was so slow, and it didn't really have a signature in what we call the Earth-directed coronagraph. So as it was coming out at us, we didn't really see much of a signature at all. As a matter of fact, we had to really count on stereo, which is kind of staring at the sun, kind of from the back, but also from the side, to watch this thing come out and say, oh, okay, there really is something big there. Plus the fact, you know, we get a little lazy around solar minimum. I hate to say that, but we kind of get complacent because the sun really doesn't do all that much during solar minimum. And so, you know, we looked at this and said, well, okay, it was a filament. There's probably going to be a storm, but it lifted off in two parts. And, you know, maybe there was some fast wind behind it that lifted, that then would chase it and maybe cause it to be a slightly longer storm. But we really just didn't think all that much about it. In fact, if I go to the other, let me do a different color. Now this is 211 angstroms. The reason why we use the pink sun is it shows a slightly different layer of the sun's corona or chromosphere, and you can actually see coronal holes a lot better. You can see really the extent of them. And you don't see filaments quite as well, as you can see here. It's dark, but not quite as distinct as it is in the brown sun, which is 193 angstrom, slightly different wavelength, so a slightly different temperature. And so a slightly different layer of the sun's atmosphere. But when we did see this thing erupt, it did have this, it did kind of open a coronal hole just a little bit. We have this finger here, and then I'll show you as it erupts. 1, 2, 3, come on, woof. There it lifts off. See how that kind of opened this area up a little bit? So we kind of had a little bit more chance for some fast wind behind it, and sure enough, that's what we ended up seeing. So that gave us a little bit of pause. We also had, prior to, we have a boom right there. You see that flare? That flare launched a solar storm that went south of us mostly. And so we knew that, okay, this might actually give us some level of storming because, well, we got one that's going south that we might see a little turbulence, which we did. And then we have this big filament that kind of lifted off in 2 parts, and it was slow. So it might be an extended thing, but everything at solar minimum is weak. And if it's moving at the speed of the solar wind, then it's going to barely be good enough to cause a solar storm at all. So we really weren't all that excited about it. But then and I'll show you one more wavelength. This is 304 angstroms, and I'll go ahead and play this. And here's the filament. This is an even longer wavelength, and you can kind of see the filament. A lot of times you can see filament eruptions really well, but see this part of the filament lifted off. That one's still stuck. You can actually see it. I hope you can see that in the thing, but you can still see part of this filament channel filled. So not everything in this thing even erupted, which was really surprising. How soon will solar cycle 25 begin? That's a totally different conversation, and we'll talk about that. Some people think it's starting already. But at any rate, because we had this leftover bit here, and this thing didn't really lift off all that quickly, we just didn't think it was going to be doing all that much. And then when we had the coronagraph show us nothing was going on, we were like, well, you know, okay, it's going to be a simple, maybe active conditions, maybe slight storming conditions. You know, and that's one of the reasons why you saw the Space Weather Prediction Center. They didn't even model it. I mean, it was a complex storm to begin with, but they didn't even bother to model the thing. I mean, no one expected this was going to be a G3. So it tells you how, you know, unfortunately, how hard this stuff is to do. Now, here's stereo. This is a side view. Let me speed this up a little bit. Okay, here's the side view of the second eruption. It's not the one that goes south of us, but we've got this big loop. Hopefully you can see that. I tried to do this earlier for patrons, and it looked terrible, so now I'm not doing the difference image. I'm just going to do the main one, and hopefully you can see a loop. And that's going to become really important in a minute. Hopefully you see, okay, here it's erupting right here, and you kind of see the loop. Come on, here it comes right here. See that loop? Do you see that kind of circle? Like almost sticking out like this. I'll let you watch it one more time. I'll see if I can see it on the phone too as it erupts. Come on, hurry up, erupt. It's coming. There we go, here we go. It's erupting. And you see that? Okay, now the reason why when you look at that, that's what makes scientists go, oh wow, okay, you can actually see part of the 3-part structure of what we call a coronal mass ejection. That is the solar storm being lifted off. And there's a reason why it has that loop-like structure. Okay, and I'm holding my daughter's favorite toy on purpose. There are solar physicists that actually call these structures solar slinkies. Thank you, Spiro. I think it's a fantastic name, and I got it from Ben Lynch, and I didn't know he called them solar slinkies, but there's a real good reason for this, and it has to do with the way the magnetic field is coiled around these structures. We call them flux ropes, typically, and because they have such an ordered field structure, magnetic field structure, we actually can predict, to some degree, what they're going to look like before they hit Earth, if we can get the configuration correct, and if they don't wiggle or move or get distorted a lot. And that's what we thought we saw here. So when that came out, we kind of said, okay, well, we've got a really nice structure. And as a matter of fact, I'll even play HAALO-CME, which is also Nariaki Nita. He's actually got a really good picture of this. Let's see if you can see that. Hopefully you can see it better here. You'll see, when does it come out? Come on. Maybe it isn't going to look too good. There it is, right there. Do you see that kind of loop structure? So it was kind of pointing like this, it seemed, or maybe more like that. And that gave us the hint that yes, this indeed was a coronal mass ejection that had a flux rope structure. And that's what led me to say, okay, maybe, just maybe, we have an opportunity to try to model this thing, or not model it, but predict what its field structure is going to be. So that's what led me to do this, and I will scoot this over so you can see a little bit better. When this structure actually hit, this is now solar wind data, and when this structure actually hit, we'd seen it up to about here. And I said, you know, this is having a very interesting field configuration, and I think I know why. Because it's a flux rope, it's one of these solar slinkies, and I can predict if it's right, if it's not distorted, twisted, or screwed up, then I can actually try to make a prediction, because the shape and the orientation of this particular structure was such that it was going to be a really bad storm if I were right. So when I posted on Twitter back on the 25th, late on the 25th, I said, okay, guys, worst case scenario, it'll look something like this and we're all in trouble. Because this was before the storming got really bad. As a matter of fact, I think this was before we reached storm levels at all. And yet I saw this and said, oh my goodness, because this thing was moving so incredibly slowly, and if it had the right configuration, we knew we were going to be in trouble. Now, how did I know this? Now, let's see if I can explain this to you. Okay. Hopefully you see this. Now, I don't know if you guys can see the arrows. This is a paper I did a long time ago. This is back in the late 90s. And I would like to say that I was the only one who did this, but it's not true. There was Zhao and Huxma who worked on this. There was also Bothmer and Schwen who worked on this. Everybody did it for a different reason, but I decided to apply it in terms of understanding the geo-effectiveness, which is basically how hard do these things hit. And, okay, all I see is electric currents. Yeah, they're not electric currents. They're actually slinkies. These are slinkies. So what you're looking at here are tubes. Okay, magnetic tubes. We call them flux ropes. And really, they have the configuration just like a slinky. Okay, rubbish. Oh, I love that. Okay, feel free. So what's cool about a slinky is that if you look at the structure of it, it's kind of a coil, right? And on the outside, if you think of these structures as a coil on the outside that are either spiraling up or spiraling down, if they're oriented this way, they're either spiraling up or spiraling down, you can actually begin to make a guess as to what kind of field configuration this slinky is going to have if it goes by you, if it goes through the phone, let's say, or your TV and out the other side. Because in these structures, as you get in the center, you have a field that threads this thing, and this field will either go completely north, completely straight up, or completely down. And that is also mimicked in whether it's spiraling up or spiraling down on the outside. The further you go into this structure, the more straight the field gets. The further on the edges of the structure, the more curly, what we call the poloidal field, the wrapped around, you know, sideways spinning field it gets. So if you pierce one of these things and look at what the magnetic field is doing all the way through the structure, if you're spiraling up, well, let's do the one that we actually had, the actual event. If the field in the middle is going straight down, and this thing is spiraling down like this, then what we've got is we've got a field that's going to be pointing, when you hit this edge of it, it's going to be pointing this way. We call that the leading edge. And then if you get to the middle of this structure, the field's going to be pointing straight down. And yet on the outside, on the back side, it's going to be pointing the opposite direction. Because as this thing spirals around, the field points this way in front, and it points this way in back. Now, in space, that means the field is pointing west in the front. In the middle, it's going to point down. And in the back, it's going to point east. Okay? And what's cool about this is that I don't know if you can see this, but this particular configuration is exactly what I just explained. We have arrows pointing this way. It's spiraling down, first of all. It's going west. Whoop, did I say west? I think it's, yeah, west. And then I had it backwards. Go west this way, and then east this way, sorry. It goes west, and then it goes down in the middle. That's the field here going straight down in the middle. And on the back side, it goes east. So the leading field is west, which is a negative BY going this direction. The axial field is a southward BZ. It goes south in the middle. And the trailing field, that's at the field at the very back of the slinky, is going east. It's going the opposite direction. And that's a positive BY. And that is exactly what I decided to post here. Let me move it again. This is the Z component. This is 0, the dashed line is 0. Anything above 0 is up, positive. Anything below is negative, south. And what we're looking at here, the white line, this is the BY component, and that's really what we care about. Anything, this is 0, once again, anything south of this is west. South of this. Anything lower than this line is west, meaning a negative BY. Anything above this dashed line is positive BY, which is east. This is the leading part of the field. This is the middle and the end, right? So leading, axial, end. So if you start down here, you're going to have a west field. If you look in the middle, this goes to 0, but you have a field here that's maximized at a negative BZ. So that's south. And I said, uh-oh, if I see it west and south, I can pretty much tell that it's going to do this and do this. So I realized at this point here, we had a solar slinky that was west, south, east. Now, I said it was a risk when I tweeted it, and there's a very good reason for that. The reason for that is we get it wrong all the time. These structures are bent, they're distorted, they're horrifyingly just a nightmare a lot of the times. And these types of idealized configurations don't always work. But I figured, we have a hurricane, and there's a lot of amateur radio operators on, that are counting on having decent bands, and if they can't count on the amateur radio bands on certain frequencies, they need to know how long it's going to be before they can count on it again. Yeah, don't worry, this video is public. I'm keeping it public. So, hi there. I'm seeing an amateur radio operator on right now, so thank you. So I decided to risk it because honestly, if I'm wrong, you guys can pelt me with olives. I'll be glad to be wrong. But the fact was, I was nervous that we could be seeing a very large storm all of a sudden. In fact, it ended up being larger than I had even thought it could be. And part of that was because of this configuration, the direction that the field was pointing, and part of it was because it was such a slow storm. It did exactly what Hurricane Lane did, which was stall and just storm and storm and storm. And I'm sorry, Will, you're mentioning something. Mention it one more time, I'll pay attention. Yeah, I am missing people on purpose because people have a tendency to get angry at me if I get off topic trying to read everybody's comments. So the image is mirrored. Okay, your image is mirrored. My image is mirrored? Oh, I've never had that. That's weird. I'm not used to that. I guess YouTube does that. Periscope does not do that. So it's all backwards on the text. I've never seen that. All the text is mirrored. The camera maybe, or YouTube. Must be YouTube. Other people say that the image looks fine. And when I did a test earlier, it wasn't a problem. Wow. I am standing on the left side of the screen. Yeah. Okay. Are all these words backwards to you guys? If that's the case, that's YouTube. That's not me. That shouldn't be a problem for you. But That's something I'll work out on YouTube. This is one of the reasons why we do these tests early. This is my very first mini course. It's my very first time on YouTube Live. So I will go back through this and take a look and see what the issue is. Like looking into a mirror. Oh, geez. I'm so sorry, guys. I had no idea. And that's strange. Okay, but I am doing this on my phone, which I do everything on. I'm far more mobile on my phone. My phone has better camera than my laptops do. So I'll have to figure that out. How to fix that. Well, hopefully I'll keep that in mind as we as we move on. That everything is mirrored to you guys. Gosh, that's terrible. Okay. Well, hopefully what we're going to get into next won't matter if it's mirrored. So let's see, where do I want to go next? Okay, so what I wanted to do next was actually show you this, in the end, what did the field end up looking like? And sorry for the mirrored numbers, but in my direction, time moves forward this way. And this is the BZ component, the southward component. And sure enough, in the end, I predicted right around in here is when I made the prediction. And sure enough, we actually did do that. Now, the second half of this thing got very messy and noisy. That may be partly due to the fact that this was a two-part eruption and this poor solar slinky did get all distorted in the end. Or it may have just been more stuff tacked on to the end of that storm. I think scientists are going to argue for quite some time where the end of this actual solar slinky was and where just normal solar winds started. Oh, thank you. You're doing great, mirrored or not. Yeah, see, some people are mirrored and some people are not mirrored. Right, but I didn't have this problem on Periscope. People did not have reverse text, so I'm kind of confused. So I will watch the replay, and if I have to, I will abandon YouTube Live if I can't figure out how to make it work right, because I can't be teaching you guys stuff if you're having to fight a mirror image. That's just ridiculous. So I do apologize. That is not something I saw when I did this, when I did a test. But then again, I didn't put up text, so maybe I wasn't paying attention. Okay, so that's the BZ component. It is what we thought it would be. Here's the BY component. And sure enough, in mind, it's less than 0. It goes from less than 0 to more than 0. So we think this structure in here, somewhere in here, is just where the solar slinky was. And that is exactly the way it turned out. It actually extended to be longer, further out in time than I thought. So either the structure was larger than I anticipated or we anticipated, or more likely, we just passed through it so incredibly slowly that it took a long time. The structure itself may not have been that big. But just like Hurricane Lane, if a storm is going to stall right over you and just rain for days, you're going to think the storm's a lot bigger than what it really is, because it just won't leave, you know? So anyway, so that's that bit. Now, let me show you what it did to the Earth's radiation belts. And this is one of the reasons why, if you know Mike Cook, why he was so upset, and he was very, very busy over the period of time. You can actually see it right there. So now we're looking down on the Earth from the North Pole. This is the sunlit side. This is the back of the Earth. And you can see, you know, radiation belts typically should be quiet. They should be green or yellow. But when you have a huge, like that's normal right there. Those are normal. And then you get something like this, and look how intense it gets. And this is what's happening. I'll keep replaying it over and over and over again. You can see the time right here. And so this is really right at the peak of the storm. The radiation belts, every time it resets, that's when we're just resetting the day. So you can see right now the intense level of the fluxes. And this is the front of the Earth's magnetic shield. And these particles in here are trapped. Now these are very energetic. These are part of what we call the I know it's an old term to use, but I always love it. It's called killer electrons, and people will wince when I say that because it's not really killer electrons, but it's just a fun way of looking at it. These are particles that are penetrating. These are electrons that are penetrating enough that they can actually hurt satellite electronics. And we have a lot of satellites that like to dwell in this area. I believe this is geosynchronous out here that's skirting the outer part of that zone. The reason why I always worry about GPS satellites, and I worry about the new constellation that everybody wants to fly, that O2B, and or O3b rather, and half a dozen others. They want to fly constellations in here in mid-Earth orbit, but you can see why I'm concerned about that. When we have big solar storms, these radiation belts get so energized and the fluxes are so huge that it becomes, yes, these are the Van Allen belts. Yes, this is the outer belt. The inner zone you can barely see in here. Notice that it really wasn't, because there's two of them essentially. The inner zone really wasn't all that energized. It does get energized to some degree, but nothing like the outer zone. And when the outer zone gets energized, it's what we worry about are the health and safety of satellites. And this goes for your Sirius XM radio, this goes for your DirecTV, this goes for trying to get GPS signals through. The satellites themselves are most likely fine, but they do suffer glitches and slowdowns and resets and all sorts of stuff. We have seen quite a few glitches, and I don't have any off the top of my head that stand out, but I have heard reports. So we were not glitch free during this period, and sadly, this is going to continue to be an issue here over the next probably week or so, because it takes a long time for these radiation belts to die down. And as a matter of fact, I probably can, if I go to another picture, let's see, do I have C's up? No, I don't have it up, but I'll pull it up in a bit. No, I don't have it up right now. But I can find it. Hold on. Hold on a second. Let's see where we are in terms of. If you go to the NOAA website, I don't know if I can even download a new version of it right now. Yeah, I can. Okay. So this right here. Now again, it's backwards, so I apologize, at least for some of you. This says surface charging. And this says internal charging, this says total dose, and this is single event effects. These are the main four types of satellite health and safety issues we worry about. And right now there's been over the past couple days, and of course this was even bigger the day before, because this is the 28th. But even before this, when the storm was hitting, which was way over there now, these yellow and red bars were even larger. I mean, almost the whole distribution here was full of red, and that tells you that it was a huge chance for surface charging. And that's because those radiation belts, like I showed you, were so massive and so energized. And we still have problems as of the 28th. Even there's prediction for the 29th. Or I mean, not prediction. This is the 29th that was still having issues. Finally, around the 30th, we've kind of come down to some degree. Internal charging actually peaks later, so once again we have these are for even more energetic particles, so we have issues there. Total dose is always a problem, but we're good. Satellites are good at being able to mitigate that. We've done a good job of learning how to deal with these types of problems. And then single event effects, that's for the inner zone, that's for something else. But these are the types of things that satellite operators worry about on a daily basis. And so when we have these big storms, you think that, oh, okay, beautiful aurora and the bands are terrible, but now everything's better and it's all good. Well, no. For about 2 weeks after a storm like this, people are sweating bullets trying to make sure things are okay and deal with resetting things and making sure that all that infrastructure that everybody takes for granted when it comes to satellites and communications, that all of that infrastructure is still working. There's a lot of stuff that goes on behind the scenes, and we are always trying to make sure that things work and they can work through anything. But, these big solar storms, they last a while, even after the storm has come and gone. So let's talk a little bit about that, if you don't mind. The Space Weather News website has all those updated charts. Yeah, these are just NOAA charts. I'm not, I'm talking about stuff that a lot of, everybody has access to. The problem is that, the average person, you look at this, and if you're not a skilled space plasma physicist, you're going to go, well, what does this mean? So it's not a matter of getting access to these charts. I'm just trying to help you understand what they mean, and if it's relevant to you, and you want to know what the near-Earth environment is inside the Earth's magnetic shield, you can take a look at these things and say, oh, okay, I get what that means. I get what that means. I get what that does. And And, you know, if you've had Sirius XM glitches, you don't have to come to me necessarily or anyone else. You can just go to the website and say, oh, well, yeah, there's obviously been a charging event or something, or, you know, maybe there has been. I mean, there's a chance that there's been a charging event. So maybe that's all it is. I don't have to call Sirius XM and say, you know, hey, what's going on with my subscription? I can just say, well, let's see if it clears up in a couple days. And if it does, then we knew it was space weather, no big deal. You know, minor inconvenience kind of thing. So that's all that's about. Okay, so now let me talk a little bit about geomagnetic, the impact to geomagnetic, or to our Earth's magnetic shield. And I've got a really good question here from Jack, who's one of my patrons. So who's at the mini course level. So I'm so grateful for him. You know, you guys help support this endeavor that I'm doing, and I'm forever grateful. So I'm going to answer one of Jack's questions. He said, what is the basis of a geomagnetic storm? That is, why does the flow of solar wind particles that interact with the Earth's magnetic field cause an upset in the geomagnetic equilibrium? And really, what he's asking about is some of the basics. Yeah, I know. I'm sorry. The cameras that I use on my phone, you know, it's frustrating. I'll fix this mirroring thing. Luckily, the physics is the same, mirrored or not mirrored. So, yeah, because I see the same thing you guys see. I see a mirrored image in my phone, but I think that YouTube would be smarter than that. And maybe they have an option that I didn't select that can prevent this from happening again. But this word says solar wind, and this is the solar wind coming in from the sun. Okay, and this is the Earth. Hopefully you can see that. This says Earth. And what you're looking at is the Earth's magnetic field. Okay, and I took this picture as opposed to some other ones simply because they highlighted two regions here, both here and in the tail. Hopefully you can see the tail. Because those are some of the most important regions that we deal with when we talk about big geomagnetic storms, big solar storms. Now, the Earth's field actually points north. Well, it actually points through, sorry, my fault. It points north up here. It points south here, inside the Earth's core. And magnetic field lines are such, hopefully you can see these arrows, that the loops come out, and when they come out in the front, they point north. And out here over here, they go south, and they come up here, point north, and they go back into the North Pole. So south in the middle of the Earth's core, out through the South Pole, the field is pointing south, it loops out, points north, and then comes back into the top of the South Pole, or top of the North Pole, okay? And it does the same thing over here. This is simply a dipole field. That's a simple dipole field configuration. You put it in the solar wind and it gets distorted. And I'll show another version of this in a minute. But the reason why I wanted to show this as being important and tasteful is because, first of all, the drawing is good. It's a decent drawing. It's showing what we call the bow shock or magnetopause. They're close. And it shows how the field actually is distorted through this boundary. This boundary basically marks the boundary between the solar wind and the inside of the Earth's shield, as they call it. And what happens is if you have magnetic field that points north here, then it's like having a magnet that's pointing north at this point, having a magnet that's south, but it has a field that is ready to either repel something that is pointing the same direction as it, or it's ready to click and attract something and combine with something that's pointing in opposite direction. So since at the nose of this magnetic shield it's pointing north, we need southward magnetic field. So the solar wind has to have field that points south. When it does that, if you think of the solar wind as a bunch of little magnets being thrown at the Earth shield, if you want them to stick, which means the magnetic fields will combine and become a single unit, then this is what you need to have that happen. And you can have reconnection, as we call it, right here at the nose of the Earth's magnetic shield. You can have it in other places, and it gets more complicated, and I won't go into that. But then you also, once you connect here, and you combine these two fields, what happens is that the earth, or the sun's, or the solar wind, all that energy that was in that solar wind suddenly gets poured into the Earth system, inside the Earth's magnetic shield. And now the Earth's magnetic shield doesn't know what to do with it all. It's got to figure out how to get rid of it. So what it does is, believe it or not, it folds some of these field lines, they break, they recombine, they fold back, and they begin to compress down here in the back of the tail, believe it or not. They compress down here in the back, and what you end up getting, this thing begins to puff out, pull out. The field lines begin longer and longer and longer, kind of like you're pulling on a slingshot, and you're pulling the rubber band tighter and tighter and tighter. It eventually pinches off back here, and then you shoot a big bubble of stuff, of energy and stuff, back down the tail, out of the system, and then this snaps back and shoots particles forward that then go into the North Pole and particles that go into the South Pole, and that's how you get the aurora. Okay? So it's a very dynamic ballet. It's very complicated, and I'll show, hang on, let me get the right, here we go. Let's see if I can do this. And I will show an example of how this works. Hopefully you can see this. So here's the Earth again, and you see all these magnetic field lines. Now remember, you're looking at something that's very similar to a slinky, again, okay? Sticking kind of in and out of the field like this, okay? And it's very springy, right? So think of a slinky that's sticking in this way and in this way, okay? And now you're watching a cut through that, and you're watching it evolve. Now I wish I could slow this down, but what you can see is that when a solar storm hits, did you see that field line bend back? Did you see it break and kind of come back and fold back over? See how it's bent and folding over? These field lines in front will break. They'll snap, and they'll go this way, and they'll go this way. And they get folded back. And as they get folded back, the wings, what we call the lobes of the Earth's shield, get bigger and bigger, and they begin to compress down this way. And they fold in. Because of the pressure, they fold in. See these lines keep coming in, coming in, coming in? And when they pinch tightly enough, what ends up happening, I think we just changed angles here. Hopefully it'll reset. Let's restart this. Yeah, replay. And when they pinch in enough, they actually will pinch off a bubble. And you'll watch it shoot bubbles. I'll let it play for a second. And you can watch these things. It stretches out, and then it pinches off a bubble and shoots that stuff down the tail. And as it does that, see how shrinky, how much it shrank back in? It's also shooting particles forward. It's shooting particles up into the North Pole and down into the South Pole. And this is exactly what happened during this storm. And every time it does that, you get an intensification of the aurora. Now this is a big geomagnetic storm. Trust me, there's a lot of other little stuff that goes on. But the basics are really what we're talking about here. And so that's why you need southward field. You need southward field in the solar wind to be able to strip these field lines off of the front of the Earth's shield and push them back, and then they can pinch down and cause this whole ballet to ensue. It's a very dynamic thing, very hard to predict. And this is why scientists have been studying this for ages, and we still don't have all the answers. So I can slow the playback down in the settings in the bottom corner of the gear symbol. I didn't realize that. Really? Speed. Let's see. How about half speed? There we go. Thank you. I did not know that with YouTube. Okay, so by slowing it down, you might be able to see this a little bit better. And I can put the link in my Patreon feed. I can put the link to this video. It's actually from the 2012 storm. There's a bubble right there. You see how the field lines let go, and then this shrinks down and becomes almost back to looking like a slinky again. But then more energy is input. It folds the field lines back, and once again, it stretches out that tail. Look at all that stuff hitting it. Boom, 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 boom. All that red, right? Look how far that tail stretches out. Right? And then it breaks off, shoots something down the tail, and it shrinks back up again. So this happens a lot during the geomagnetic storms. This is why we fly so many missions in the tail and everywhere else. We're trying to capture that very special little region that moves around so much, that place where the reconnection happens. And it's such an elusive thing to find, and we've been fighting ages and ages. We keep getting really close, but it's very rare that we actually get a chance to actually fly right through it and sample what's going on. So hopefully, but these are useless simulations. No, they're not useless, because it allows scientists to think further. This is, sure, they're not real. None of this is real because we have numerical diffusion, we have simplifications and assumptions that we make. But the good people, the people that pay attention to this stuff and use this in a scientific endeavor, what they do is they remember what the assumptions are. And they say, okay, I would love to think it's like this, but it isn't because I made this assumption and that means that's false. But what it does is it allows the scientists to think further than they ever have. And it allows us to have discourse and arguments about whether we think something is real or not. And that's the way science moves forward, is that we argue with each other. We don't agree. Most of us don't agree at all on things, but we come to a consensus. And that's how we push the field forward. And if we didn't do illustrations and models like this, then we wouldn't see where we got it wrong, let alone where we got it right. So I disagree with you when you say that these are useless. They're not. They're instructive, just like everything else is in this life. So hopefully that, the solar wind is the heliospheric current sheet. No, the solar wind is not the heliospheric current sheet. The solar wind is part of it. We pass through the heliospheric current sheet all the time. That's what a sector boundary crossing is. So unless you have a, there's a lot of misinformation that's out on the web and everywhere else, and there's a lot of good information out there, but you just have to be careful how you take it. If you try to take everything for granted and think you know more than you do, that's when you get yourself in trouble. That's why you always hear me say things like, oh gosh, I hope I do this right, or this is not my area of expertise, because it is so easy to get so many things wrong and make the wrong assumptions and think you're smarter than you are. But that always leads to trouble. That's one of the reasons why scientific argument and going to meetings and writing papers and having peers tear your work apart is so important. And if you ever were on Twitter and see us scientists arguing back and forth, well, that's what we're doing. We're just bringing that scientific debate out into a public forum so you can watch it and perhaps participate. Because we honestly want to hear from everybody. And if somebody makes a really astute comment or insightful remark, we're going to respond to it, because you might give us a really cool idea that we hadn't thought of before. Okay, so what I'll talk about a little bit more is, because I've been on here for about 42 minutes, so that's quite a bit. Okay, so what I'll talk about a little bit more is some insight into the K indices and why, because there's so many bad drawings, why the K index is different in different locations, right? Because you've got a KP, but that's different than a local K. Now, why does a local K vary so much? And Andreas actually sent me this question. Why do the K indices differ so widely in a 3-hour period between, let's say, Boulder and College? So let me talk a little bit about that. And hopefully, again, I'm sorry that it's mirrored, but hopefully you can see this. This is an arbitrary drawing of the Earth in terms of its orientation. You have a pole, a geographic pole that's going through this solid line here. That's the geographic north and the geographic south. It's also the axis upon which the Earth spins and rotates. Then this dashed line shows where the Earth's magnetic field is. Geographic north and magnetic north don't line up. They're not exactly, they're tilted from each other by a certain amount. And that's important, because that actually gives us seasonal variations in solar storm effectiveness. And it gives us a couple other things, but everything in terms of space weather is really ordered according to the magnetic field. We don't care what your geographic latitude is, we care what your magnetic latitude is. We don't care what the UTC is, what the universal time code is, or time constant is. Constant time, what does C stand for? I forget. But we don't care what universal time is. We care what your local magnetic time is. And about 11 degrees west at my location. Right, there's 11.5 degrees, it says right here. And so because everything is ordered by the magnetic field, we have to look at things in a particular way. And when we look at magnetic indices, so we look at the K index, believe it or not, that is derived from magnetometers on the ground. So it's measuring the Earth's magnetic field and basically how wiggly it is, right? How springy is the slinky. Because I mean, you know, if you make this kind of like the Earth's magnetic field, right, this little donut, right, it's very springy, right? This is the Earth's shield. It does this all the time. I mean, it can do this all day. But anybody who knows anything about magnetic fields knows that if you have anything conductive in a magnetic field that's doing this and moving, ooh, you're going to generate currents. You're going to generate electric potentials and currents. So that's why we measure this stuff so much, and this is one of the reasons why the national power grids always care. But Canadian power grids and grids at higher latitudes are oftentimes more susceptible than grids at lower latitudes. The ionosphere, the upper atmosphere, is oftentimes far more disturbed at high latitudes than at low latitudes, right? And why is that? And the K indices show that as well. Why is that? Well, it's hard to find pictures of the Earth's magnetic field that are drawn properly. A lot of times people draw these magnetic field lines and they show them all going into the pole, like all of the magnetic field, it just comes out of the pole and the North Pole and the South Pole, and there's nothing going on down here. And that's just not true. The reality is that these magnetic field lines from, and this is a simple dipole field, actually map to different latitudes, as you can see. So high latitudes, lower latitudes, in this case mid-latitude, and you even have ones that are even lower latitude. But there's something interesting as you look at the latitude which these magnetic field lines map to, as we call it. The ones that go to the lowest latitudes, right, they're inside, protected. If you think that this is an onion, for example, look how many layers you have to get to. If you're something on the outside where, say, the sun is over there, you're blowing solar wind at this structure, look how far you have to go to get to this field line, right? Think you're going to make it? Probably not. Only the biggest storms can actually slam or compress or change something so that low latitudes will actually even notice. Now, they might feel a little wiggle here and there. That definitely does happen. But are they going to be as disturbed as the outer layers that are being shredded? Right? No. But those outer layers map to the highest latitudes. As a matter of fact, all of this region up here inside the auroral oval is open. We call that open field. It's actually open to the solar wind. So that's where we get aurora. That's where we get all sorts of changes. That's where we get radiation storms. That's where we get all sorts of havoc, because basically there's no protection for that region up there. That's why people on polar flights, you worry about that, because they're so vulnerable to solar radiation storms and cosmic rays. But as you get to lower latitudes, you get more and more layers of protection, so that by the time you get down close to the equator, you're looking pretty good. I mean, you don't have a lot going on. And that's why we always warn, okay, aurora will be at high latitudes, but not down at low latitudes. In actuality, sometimes you can actually have a storm that causes some disturbance and it wiggles the lower magnetic field lines and causes enough upper atmospheric disturbance that it actually helps. It actually stabilizes the upper atmosphere and makes it better for radio propagation sometimes, and definitely for GPS reception. It actually, because there's some other issues that go on here that destabilize it, but those have to do more with Earth than to do with space, with the sun's influence. But I won't get into that. So this is the reason why you worry more about the high latitudes and why you see far more disturbance in the high latitudes than you see at low latitudes. And if I go to, I won't bother that, but I will show you this. So here is, for example, this was the big solar storm that we had, right? And again, but this is Boulder, this is Fredericksburg, this is the planetary KP, and this is College. So these are 4 different magnetometer stations, and they've simplified the magnetic field to make it just look like K indices. So these are local K indices, and this is the KP. But if you notice, they're very different, right? College by far is the most active. And I don't know if there's a calibration problem with this one, but it's definitely the most active. It often will jump to multiple storm level. Here's a KP of 8, or a K of 8, a local K of 8. Whereas Fredericksburg, they barely got to a K of 6, or 4, 5, and 6 at this same period. And so the planetary average, right, averages all of these mainly over, I think, the United States. We have by far the most. But there are local Ks all over the world, because they're just looking at magnetometers all over the world. And of course, planetary K, I think the KP, I'd have to see how many stations are actually averaged into a KP. But when people look at the KP, they really do have to understand that it's a global average. So you have certain stations like Fredericksburg that are not going to be rattled as much as something like College. And this is why I tell people to always look at the local K in their region. Not because she understands the geomagnetic storm affected its behavior. Oh, I have no idea what you're saying. So in that case, if I actually go, see if I can actually go to, yes, to the USGS. So here is, if I pull this up here, here are some actual field readings at USGS. Now these are some of the components and the stations that go into the K index, okay, local Ks as well as the KP. And this is during that solar storm. Now you can see these numbers here. I don't know if you can read them. They may be backwards, but you're seeing 17,000, 19,000, 13,000 during these periods. They were incredibly intense. And that's why but if you notice, they're all very different. I mean, here we're 21,000, here we're 23,000, but the others were 19, 17, 13. But you can see the structure actually changes as we go through these traces. Okay, they don't all look the same. And the reason for that is the latitude dependence, because every single one of these is representing a set of field lines, and they're all getting wiggled quite differently. So that's what actually makes the huge differences. And scientists can actually look at this stuff and make again, get an understanding as to even where in latitude a particular storm is happening, if there's pulsations, because the Earth can ring like a bell. There's all sorts of different things that we study using this type of magnetometer data to understand and probe not only the ionosphere, the upper atmosphere, but obviously the magnetosphere way out, because things map way out. Now, this is not my expertise, and I know a little bit about it, but not enough. I know enough to be dangerous, not enough to be right. So, that's what we're dealing with here. Okay, but that gives you an idea. And some of these wiggles can actually change and go the opposite direction, like there. Here's a perfect example, right? You've got two magnetometers at two different locations. Well, that's actually a component. No, those are two different ones. We're looking at the same H component, the horizontal component of the field, in two different locations, and they're radically different. And that flags a scientist that, okay, something's happening at the latitude between these two stations. So there's all sorts of really cool things that we can do to understand this stuff better. And I think with that, I have pretty much answered all of the questions that that people have asked of me. So if anybody has questions on the chat, I am very willing to answer a few more before I sign off, okay? Hope to get back out with a camera for Northern Lights in Northumberland. Yes. Oh, and let's see, okay. I can't read that. It went by too quickly. What do you think about the theory that earthquakes are electrically driven? The thing with earthquakes, and I answer this question so often, is the way that earthquakes are driven is so incredibly dominated by earth processes, tectonic processes, geologic processes, that if there is a space weather component to it, we have no hope of sussing it out until we understand the primary source of earthquakes. And then we can remove that effect, and then we can take a look at what's left, what we call the residuals. Once we're able to remove that primary driver of earthquakes, and then we can look to see what's left, we might actually see a space weather component. Wouldn't that be cool? I think space weather physicists would love that. But we don't have any hope. And you know how we don't have any hope of that right now? We're waiting on the geophysicists. The reason why we don't have any hope of understanding that right now is that even when the sun goes quiet, earthquakes are still everywhere. They're everywhere. And it's like, if they're everywhere when space weather is busy, and they're everywhere when space weather is quiet, how can we have a hope of trying to suss out if there is a space weather component? And just simply because earthquakes corresponded to space weather events just means earthquakes are everywhere. They're just everywhere all the time. It's just, I mean, you know, they happen so frequently. A lot of times they just happen in the ocean, and so people don't report on them. But they happen so frequently all the time that if you want to find a big quake, you can. Anywhere, anytime, whether the space weather is quiet or loud. So let the geophysicists do their job. Let them find out the primary driver and then remove it. So us space weather physicists can actually get into the brass tacks and find out maybe there is some correlation. But, you know, I keep getting hit by people saying, oh, you know, you're just hiding something. Oh, you space physicists, you guys, you're just evil. And you never, you know, you're just hiding stuff from the public and you know more than you do. Guess what, guys? We don't. We really don't. We just are held to a very rigorous standard as to how we do research. And we can't dig into something that won't allow us to. And until we figure out what the primary driver is of earthquakes, we've tried. I mean, people have been writing papers on this stuff since the 1800s looking for correlations, and we can't find ones that are robust enough to say, yes, let's study this. We have to wait for the geologists and the geophysicists to figure it out first. And then we can attack the residuals and look at what we call the lower order effects, which may be space weather. We don't know. Oh, thank you. Okay, I appreciate that, guys. Okay, so I'm sure I missed 1,000 questions, but you know, anyone else? Let's see. I follow another YouTuber. I know there's tons of them, and you know what? Again, I'm not going to bash anybody who does space weather, because space weather is at a state right now that is it's so the awareness needs to be raised. If you look at, for instance, my forecast that is going to be out on YouTube here in just an hour or so, I'll talk about Hurricane Lane. I'll talk about how amateur radio was affected. I'll talk about how GPS was affected, and I'll give you specific examples. Okay, I'll talk about that in a second. Solar cycle 25, and it's so critical because space weather is becoming so important to us in our technologically advanced era. So I'm not going to knock anybody who does space weather, and by continuing to talk about earthquakes, you're always going to keep it forefront in our minds as scientists, that you're not going to let us rest until we figure that out. And that's a good thing. The only part that I have an issue with is when people say that because we don't have the answers you want us to have, that we're evil, and that we're hiding, we're working for Big Brother, and we don't have the public's best interest at heart. And you guys have no idea how much that actually does hurt. I mean, of course we have your best interest at heart. We're part of you. We're public too. And we're just doing the best we can with what we've got. But there are rules that we have to follow that are based in physics and in scientific discovery, and the way the scientific method is used and applied. And that's what we're trained in. And so it limits our ability to just make wild accusations and say, yes, because we see a correlation, that must be the truth. Because correlations don't mean causality. And so we have to be far more rigorous. So we can't go forward and say, yes, there's a connection, because honestly, we can't prove it. But you are forcing us to remain on task, and eventually that question will be answered. I don't know if I'll be alive to see it, but that'd be great. That'd be really great. Okay. Oh, it's the sun. Yeah, I know. Sometimes you see faces in the sun. It looks pretty amazing. Okay, so solar cycle 20. It doesn't come up. But this is this is region 2719, I believe, and then 2720 comes up here. But there's a actual hole. I mean a neutral line. They're in separate hemispheres, and so normally, the polarity would be reversed across the hemisphere. So if you saw black and white on one side, on the northern hemisphere, you'd see white and black on the southern hemisphere for the sunspots. They are opposite polarities of each other. But these two were the same. So we knew that this one was one that was from the current cycle. But then when we saw one that was reversed and had the polarity that was the opposite of what we expected, in other words, black was leading white or white was leading black instead of the other way around, that's how we knew. It's like, oh, hey, this is a sunspot that is from a different cycle. Now, this wasn't the first one we've seen. We started seeing them back in December of 2016. And we've seen 2 or 3 or 4 since then. But this is the first one that's had persistence that I can tell. We've had ones that came out and then we watched them for a little bit and then they disappeared again. But this one actually rotated onto the sun's backside. So we're watching it now. And it's going to be very interesting to see how this thing evolves, if it stays alive or it disappears or what it does. And if we start seeing more and more of them, then we're definitely going to be moving toward to the next cycle. I think it's 50% of the sunspots have to be from the new cycle before we officially call it the new cycle. But some scientists say it's already here. Some very famous scientists have said it's already here. So okay, I missed that. Glad to see Science Woman, don't get it wrong. Oh, okay. No, I don't take offense to that. I appreciate you recognizing that, yeah, women in science. I should see some of the YouTube comments I've gotten where people would just rip on me for being a lady. And it's like, oh, women don't know anything. Okay. I don't have a response to that. It's just, all right, everybody to each his own, I suppose. So, are there going to be any hurricanes in Florida? I don't know. Ask a meteorologist. I am a space weather person, so that doesn't help you. I don't have enough skills in meteorology yet. I'm going to be moving toward that, though. I want to be able to blend the two fields a bit, and so I need some training. Alongside the training that you all have given me as being reporters in the field. Don't let men get down on your intellect. Yeah. Yeah, well, society has its biases, and it's okay. I've lived quite a few years on this planet. I've dealt with it, as long as I can remember. So I'm used to it by now. So it's okay. We probably hit solar max somewhere around 2024, maybe a little bit earlier, because it looks like we're going through solar minimum fast. So, affecting Earth's climate. Oh God, that's so hard. Climate science is hard. What I will say is the sun is, if anything, if it's affecting anything now, it's giving us a reprieve. There have been times when the sun has been far more active than it is now, and even over the long term. And so, if it's doing anything, we're actually becoming complacent both with space weather, and it's actually helping kind of give us a little bit more time to kind of get ourselves under control with fossil fuel burning and all that kind of stuff. So everyone knows the sun has nothing to do with climate. Right, if the sun turned off tomorrow, we'd never notice, and definitely wouldn't notice in 100 years. You're absolutely right. How silly of me. I should go back to school. What about the grand minimum? Okay. Could there be a grand minimum coming? Possibly. We just know it's not yet. And as a matter of fact, I think people have seen the turnings of even the next cycle after this. So at least for probably most of the rest of our lives, we won't have to worry about sunspots going away anytime soon. Oh, channel could use some moderation. Yeah, well, I'm a one-woman show, so I just kind of, smile. So anyway, guys, okay, I will say goodbye unless there's any final questions. I will bid you all adieu, and thank you so much for such a wonderful live stream and excellent questions. So, okay, yeah, I guess sign some of you guys up as moderators. Hey, contact me. Contact me on Twitter or contact me via YouTube, and I will chat with you about it. Okay? Thanks, guys. I appreciate it. Wonderful talking to you. Okay, bye.